We are going to have the next topic on differential and operational amplifiers. We have done small signal amplifiers, either common emitter, common base type or common source, common drain in FET and MOSFETs. The knowledge which we have gained out of these amplifiers, that has been used for realization of more advanced amplifiers, and differential and operational amplifiers are an example. Now, these operational and differential amplifiers, they are available as integrated circuits. They are designed on a chip which is much more economical and convenient to use. So, these are complete circuits where externally only few capacitors and resistances may be required for the desired performance, but as such they have complete circuit on the chip. So, they are available as ICs, integrated circuits. In integrated circuit, large value capacitances are difficult to fabricate. So, capacitors having values higher than say 50 picofarad, they are avoided. Capacitors higher than 50 picofarad in value, they are avoided on the chip. Bypass capacitors and coupling capacitors normally are in microfarad range. That means 100 times more than 50 pf. So, these circuits, differential and operational amplifiers which we are going to use, they are avoiding this capacitor coupling. These are direct coupled amplifiers. You remember when we talked about the coupling used in amplifiers, there are three kinds of couplings which are used: RC coupling, very widely used, direct coupling and transformer coupling. Here transformer coupling is having restricted applications because it is bulky and there are other features associated with them. They cannot be integrated. These transformers are not integrable at present. So, their use is restricted. And direct coupled, where for coupling just a direct conducting path connects the source, for example, with the amplifier, no need of coupling capacitor, and hence frequency response obviously will be different. There is no restriction on a smaller frequency. These amplifiers will work at as low a frequency as 0, that means for DC also they will work equally well as for several kilohertz, several few hundred kilohertz and so on. Now, so these are direct coupled amplifiers available on integrated circuits. First we take differential amplifier, and after finishing that we will take much more widely used amplifier circuit, that is operational amplifier. Operational amplifiers in short and more popularly they are known as op-amps. Op-amps. And why they are called operational amplifiers or op-amps? Because these amplifiers can be used for summing, subtraction, multiplication and integration, differentiation, all kinds of mathematical operations can be realized using these amplifiers, and that is why they are called operational amplifiers. First we take a differential amplifier. Differential amplifier. Differential amplifier is very different from conventional small signal amplifiers. These are actually composite amplifiers, and in differential amplifiers there are two inputs. It has two inputs, and that means the two signals at the two different inputs can be applied simultaneously. And then most important, why it is called differential amplifier or sometimes difference amplifier, but most popularly it is called differential amplifier, because when we apply two signals, difference of the two signals is amplified and is available at the output of the amplifier. I repeat, differential amplifier has two inputs, two signals, input signals can be applied, and this amplifier is capable of amplifying the difference of the two signals, meaning any signal which is common to both inputs will be filtered out automatically. Only the difference will be amplified. In real time situations, there are many conditions where, for example, noise generated by motors in an industrial area, if we use the conventional amplifier, then actually those signals will be picked up and they will also be amplified, unless extra precaution is taken to reject them. Here that will be automatically be taken care of, and noise will not be amplified and will be filtered out by the difference. Only the difference of two signals will be amplified, whatever is common to both, that is not amplified. Now, what is the basic circuit? First, let us talk about the basic circuit and why it is so important, why we should give so much importance to differential amplifier. Those features we will bring out. So, the circuit is, the basic circuit for differential amplifier is basic circuit is this. This is the basic circuit of differential amplifier. There Q1 and Q2, these are two transistors, and they have been connected such that they have a common emitter resistance Re, and they are connected at the resistance Rc also. In fact, these are the result of two amplifiers like this. these are the two separate amplifiers which are coupled in this fashion. You remember when we talked about biasing of transistors, that the emitter bias which makes use of two power supplies, one positive plus VCC with respect to ground and the other negative minus VEE with respect to ground. This reverse biases, this is NPN transistor, NPN. So, this reverse biases the collector and this forward biases the base emitter of the NPN transistor. Now, this is forward bias, this is reverse bias. So, this is amplifier where it will work in the active region of the IV characteristics, and when we couple the two, this is the shape which is the differential amplifier. When we say that two adjacent emitter bias circuits have been coupled together to give differential amplifier, this is the differential amplifier. Here the output is taken from two collectors. While other possibilities exist, we will talk little later, but commonly this output is taken from two collectors. Between these two collectors, whatever is the output, that is taken. So, the output is here V 0. Normally we take from collector with respect to ground. Here we take between, the output is taken between two collectors. Symmetry of this amplifier is a essential part for proper performance. It is symmetrical across, it has a almost a mirror image of this Q1 to as image is Q2. So, the two transistors have been constructed as close to be identical as possible technically. Now, this becomes very clear that when everything, when two signals you apply of identical magnitude, same magnitude, then this will be available at C1 in the amplified form, and because the signal we are taking for as an example only identical to this, the same voltage will appear. So, between the two collectors when we take output, the output will be 0 as it is supposed to be, because the signals, the whole signal is common to both, and hence output will be 0. So, this is the way the differential amplifier works. It has very wide applications, and there are several other associated reasons that why we should study the differential amplifier. Now, the salient features are of differential amplifier are, as I said, the difference of two signals Vi1 and Vi2 can be amplified. So, as a we can use it as a difference amplifier. Second is by grounding one of the two inputs. If one input is grounded to 0, then we can use it as any other amplifier. So, this can be used as a single signal amplifier. It can be used as a single signal amplifier by grounding. By grounding we mean by making 0 the other signal source, other input signal source. And since it is direct coupled, it can be used, it can be used to amplify signals of very low frequency. We can amplify signals of very low frequencies, including 0 frequency, and when omega is 0, we can use DC signals also. And very important is the operational amplifier, which has almost revolutionized the system design today, and hardly there are circuits which do not make use of op amps, either digital or analog circuits, where op amps are not used. In all circuits, op amps are very widely used. So, differential amplifier is the first stage of operational amplifier. Differential amplifier is the first stage. Operational amplifiers are multi-stage amplifiers. We will go in great details how does it work and all that, but the first stage is a differential amplifier. So, a differential amplifier is the first stage in op amps, operational amplifier. And then there are other features also. For example, as we will see that input impedance of differential amplifiers is very high. It is several hundred kilo ohms or even meg ohms, in spite of the fact that we construct them by using bipolar transistors. So, these are the salient features that make differential amplifiers very popular, and we should study them in greater detail. Now, basic circuit we have talked. Actual circuits are not very different from this circuit, and that we will be drawing. Now, for any amplifier there are two types of analysis which we are supposed to carry. One is the DC analysis, other is the AC analysis. DC analysis is done to ascertain ICQ, that means collector current at the operating point, and VCEQ, what is the drop across the resistor between the collector and the emitter. That is to be studied, and from there we can take out the design procedure, that how to choose the value of RC or RE, very simple. So, this comes under DC analysis. Then we will carry on AC analysis of differential amplifier, in which we will find out what is the amplification factor and on what parameters the amplification of the differential amplifier depends, and there we will see that how does it act as a differential amplifier. And from the AC analysis we will come to a very important point, that these two inputs, input 1 and input 2, they are also not identical, they are distinguishable, and we will see that one is called inverting input, the other is called non-inverting input, and why we call them, the reasons will become clear when we go for the AC analysis. So, first we take DC analysis of differential amplifier. DC analysis of differential amplifier. In the differential amplifier, in the DC analysis, the AC sources have to be grounded. So, the actual, this is the situation. This is the first source Vi1, Vi2, and this is the source resistance Rs. Rs is source resistance of this signal source, which is normally small. This can be a oscillator, or it can be, for example, a mic or some other device, and every device has a impedance, and that is called source resistance, and normally these are small. For DC analysis, which currently we are carrying out, AC sources, they have to be grounded. We are not going to consider them. So, then what will be the circuit which remains? That is this. Here these are all, both are grounded, and then the circuit will be when we ground them, we leave the Rs in the circuit, which we may drop at some stage, because they are normally very small resistances, and here IC, and since we are saying circuit, this is very important, circuit is symmetric. So, here this is also IC, and then from Q1 IE will flow, and from here also, from this emitter, IE will flow. So, this IE and this IE, that means from this tail to IE will be the current. IE from here, IE from here, and both will go through this resistance, emitter resistance RE, and hence 2 IE current will flow here. Now, let us analyze this circuit, and this voltage VBE as usual, this also is plus minus VBE. We apply KVL, Kirchhoff's voltage law, to the base emitter loop. Base emitter loop. When we apply, we get this RS base current, here base current, and plus VBE plus RE and into 2IE minus VEE. This is equal to 0. We sum up all the voltages here. For symmetric reasons, only this one is sufficient to do, instead of rather doing the same process twice. Only this is sufficient. The analysis for one transistor currently is sufficient to be carried out. And then we apply in this equation using beta the current gain. These are common emitter amplifiers as usual. So, beta is IC by IB actually, sorry, IB is equal to IC by beta, which is equal to, because IC is same as IE, so this is IE by beta. So, IB we replace with IE by beta, and one IE is already here. So, then from this equation what we come, IE is equal to VEE minus VBE by twice RE plus RS by beta. This is the expression for, as I said in the beginning, that the objective of DC analysis was to find out ICQ and VCEQ. What are the value? VCEQ, that is the voltage drop between this and ground, here this voltage. So, these have to be found, and for the symmetry region we are doing it only for one transistor, this we have said. So, this is the IC. Now, here the RS is small, as I said in the beginning, the source resistance is small, and RS by beta will obviously be very small, and since RE is very large as compared to RS by beta. So, RS beta we can drop, and the expression IE, which is same as IC, and in the absence of any signal, this is ICQ, and that is VEE minus VE. This is 0.7 volts for silicon device and divided by 2 RE. This is the current. ICQ is VEE, and many times this VBE is dropped in comparison to this, and this does not incur much error. But anyway, this is the quotient current, and if we choose the current, we can find out what value of Re is required, that will give that much current. Or if Re is fixed, then what will be ICQ, that can be known in the circuit. And then this Re, this actually is like a tail. So, current through Re, current through the resistor Re is called tail current, and often written as IT for tail. And how much is the current, tail current? 2IE. And why 2IE? Because IE will go from transistor Q1 and I will go from transistor Q2. So, the tail current and IT, the tail current is equal to 2IE, or IE, the emitter current in each transistor will be half of tail current IT. This is another useful relation. And then we have to find out what is the voltage drop here, which is VCEQ, that we have to find out, and for that we can apply again the Kirchhoff's voltage law, KVL, to find out VCEQ. We apply Kirchhoff's voltage law, summation of voltages at the collector circuit. When we do that, we get VCC is equal to RC IC plus VCE plus VA, where VA is the voltage at this point A. What is the voltage? So, we have taken this, but we know, this is important, what is the voltage here. At this point A, what is the voltage? This is plus minus VBE. This is also plus minus VBE. So, what is the voltage here? These two voltages VBE, they are in parallel. So, voltage will remain just single VBE and with minus sign. So, but VA is equal to minus VBE, because VBE of Q1 and Q2 are in parallel. So, in parallel the voltages are not summed up, only in series they are summed up. So, this is the voltage. So, then we substitute here and we get VCE, which is same as VCEQ, and this is equal to VCC plus VBE minus RCIC. this IC is the same as ICQ. So, this is known, several parameters in this will be known, VCC, how much battery. Now, normally it can be 5 volts or 9 volts or 12 volts. So, we know this, this is known, 0.7 volts for silicon, most of the, because integrated circuits are mostly on silicon. Some very high devices are on gallium arsenide, not a single IC is formed with germanium. So, VBE is equal to 0.7 volts for silicon devices. So, this is known, and hence the value of RC, keeping how much voltage we want. So, out of the two, if one is known, the other can be calculated. Now, this is the DC analysis, and this DC analysis is applicable for this particular, this differential amplifier, and this is important, and all its variations which are possible. This can be used in more than one way, this differential amplifier. So, this analysis is applicable to all the variants of this differential amplifier. Now, what are the variations within this differential amplifier? What are the variations possible? The variations come from the fact from where we are taking the output. When we take output from two collectors, this is called balanced output. So, what is balanced output? Balanced output, that means when output is taken from two collectors, this is balanced output. And in fact, output can be taken from one collector C2 with respect to ground. This is one possibility. Other possibility is when output is taken from one collector, normally C2 collector of this Q2. From here we take the output from collector of Q2 with respect to ground. We call it unbalanced output. Unbalanced output. Similarly, we use two input signals, so we can get a balanced output or unbalanced output depending on the application. Besides that, we can have single input or two inputs. There is no restriction that essentially we will have to use two inputs. We can ground one and the other we can use as an amplifier. So, this gives rise to different variants. So, 4 configurations of differential amplifier are there, and these 4 variations are 4 configurations. Four configurations of differential amplifier. The one is dual input. That means we are using two input sources, dual input, balanced output, differential amplifier. Dual input, balanced output, that means that we are taking output, balanced output from two collectors, and the two sources we are using. So, dual input balanced output differential amplifier. Then we have dual input unbalanced output differential amplifier. Here the output we take from this collector with respect to ground, and we are using two input signals. So, dual input unbalanced output differential amplifier, and similarly we can use a single input balanced output differential amplifier. So, here we are using only one input source, and we will be taking output from the two collectors. And finally, single input unbalanced output differential amplifier. In this, single source is to be used, the other input source will be grounded, and output is taken from collector of Q2 with respect to ground. So, these are the four configurations. Some of them are widely used, others not, that we will be taking. Now, we take the general analysis, AC analysis of differential amplifier, and then from that general analysis we will take important parameters for these amplifiers also. So, general analysis means dual input balanced output differential amplifier. So, this we are going to do. So, AC analysis, general, that means the first case dual inputs balanced output. For satisfactory performance, gradually as we learn more and more about differential amplifiers, their salient features will also emerge, and we will come to know many detailed things about the differential amplifier. Now, for satisfactory performance of differential amplifier, the tail current has to be constant. The supply of constant tail current is essential for the proper functioning of the differential amplifier. Constant tail current is required. How we provide? So, we will elaborate in better designs this resistance and this battery, we can elaborate by some other arrangements which will be providing a constant tail current. So, this is essential. So, we assume that a constant tail current, in the circuit. So, this RE and VEE arrangement can be replaced by a constant current source. Constant current source replaces them. So, what will be the circuit? The circuit will be this is the we have replaced that RE by the constant current, and that is IT. IT is constant current, and this is constant current source. Which supplies constant current. Now, we perform AC analysis and we apply the rules as we have been talking all through, that for AC analysis the DC voltage sources have to be grounded and AC current sources have to be open, or the DC voltage sources have to be grounded and DC current sources have to be open. I write here for AC analysis, the rules are, which we have talked many times, that VCC, the DC voltage sources have to be grounded, and because constant current source we are using for the first time, so we should write that constant DC current sources are open. That means they form infinite resistance open for AC signal. This is grounded and this is open. Open means that no AC will propagate through this path. So, when we ground this and we open it, and these resistances RS, they are small resistance. So, we can neglect it in this analysis to make the analysis bit simple. So, we neglect. Then what is the circuit? The circuit becomes this. Open for AC. Actually, we need not to show it, but still as a this is customary to leave them like that, but remembering that they are open. These are the sources Vi1, this is RC, this is RC, and this is Q1, Q2. Now to have, because now we have more than one input source, so to study the effect of two sources on this in this circuit, we apply the superposition theorem. Superposition theorem. And what is superposition theorem? That first we apply only one source, for example Vi1, the other source is grounded, and we will study the circuit, we will study, we are interested in gain. So, what will be the gain and what will be the output because of only one source, that we will study. And then this we will superimpose on taking this as grounded, and Vi2 will be taken as active. I repeat, to study this differential amplifier in which DC source have been grounded and this constant current source is open for AC, that means no AC will propagate here. To study this, we apply the superposition theorem, and superposition theorem is that we take one input signal as active initially and we study what will be the output, what will be the gain. Then we keep that result and then we take the first one, we ground, and we take the other input source as active, and so we study that. Then we apply the superposition theorem, which says that the net output from these two sources will be the algebraic sum of individual contributions. That is this that is the way this analysis is to be done. So, we will apply the superposition theorem, and from here we will come to very significant point, that one of the inputs is a inverting, that means the output will appear out of phase with the input signal, and the other will be non-inverting, that there when the signal is applied, that will appear without any phase change. So, all these details will come out of this analysis, AC analysis of this amplifier.